Welcome back. In this part 3 of our Dynare tutorial, we're going to talk about estimation in Dynare. Specifically, we'll talk about Bayesian estimation using the Dynare tools. The first thing we should do is refer back to our model equations and remember the model that we're working with. We have a log separable utility function and a Cobb-Douglas production function with a aggregate productivity shock process Z. We have our characterizing equations of our model and some definitions. And now that we've reviewed that, we can go back and recall our stochastic mod file that we wrote last time, and specifically we'll remember the various blocks: the preamble, where we specify our variables, including predetermined variables if we have them and if that's our preference, our exogenous variables, and our parameters. We initialize our parameters, we specify our model block, we have an initial value block along with a command that tells Dynare to compute the steady state for us, our shocks block, and then our computation. In our computation here we asked Dynare to do a stochastic simulation for second order with a second order approximation, 40 period impulse response functions, and 2,000 periods of simulated values. What we'll do now is rework our model, or our mod file, to set it up to do some estimation of these parameters that we initialized before. To do that, we obviously need to bring data into our model. So the first thing we'll talk about is telling Dynare which variables are going to be our observable variables. We'll do that just below our shocks block, before computation. After our shocks block, we'll include the command var obs for variable observed, and we'll just take output as our observable variable. Before I go any further, I'm going to save this as a different file, and we'll call it, we'll just make this our estimated version. Although I didn't save it as a mod file, so now we're set there and we can come back and continue. Alright, so we've told Dynare that the observed variables that will bring data for are, in this case, just the output variable. Now sometimes you'll have data that you've filtered or detrended or done something else with, and so you might need to add auxiliary variables along with equations that map from the observable data to your model. For instance, if we were to take a first difference of our output, and that was what we were going to bring as our data, and we might want to include a variable called dy that equals just y minus 1, and we'd include dy up here in our variable list, and our observable variable would then be dy. Mapping from your model to your data will depend on the specific data you'll bring to bear in the specific estimation that you'll do. In our case, we're just going to use output. So now we've adjusted back for that. Alright, the next thing to talk about is how many observable variables you can use. And the rule of thumb there, not even the rule of thumb, but the actual rule, is that you can't have more observable variables than you have shock processes. This has to do with identification in the estimation. If you have more observable variables than you have shocks, then you don't have enough degrees of freedom, essentially, to account for the fluctuations observed in the data, the random fluctuations of the data, which get put into the shock, the realization of the shock processes. Okay, so now that we have our observable variables specified, we need to talk about Bayesian estimation. When Dynare does Bayesian estimation, it will obviously require us to specify a prior on each parameter that we want to estimate. The priors that Dynare allows are the normal distribution, the gamma distribution, the beta distribution, the inverse gamma distribution, and the uniform distribution. There are some others that it allows, but those are the only ones I'm going to mention here. So the next thing we need to do is tell Dynare which variables, or which parameters rather, we're going to estimate. And we do that with the estimated params block, which we begin with estimated params followed by a semicolon and end with an end command, as we usually do. Now, the estimated parameters that we want to estimate in our case, let's estimate beta, and we'll also estimate the standard error, the standard deviation of our epsilon innovations, the white noise shock process that comes into our aggregate productivity shock. So this is the format for the estimated params block. We'll specify either the parameter or the standard error, or we can actually also estimate the correlation between variables as well. But we'll stick with these for now. So after we specify what we'll estimate, we follow that with a comma, and we tell Dynare the prior. So in choosing a prior, there are a few things to consider. The first thing is the support for your prior. For instance, beta should lie between 0 and 1. Other parameters might be strictly positive or non-negative, while other parameters will take have intervals on which they are defined and not defined other places. And finally, you might have a parameter that's has support of all of R. So this this first question will determine in many ways what prior we'll end up using for our parameter. For instance, we have beta that's defined between 0 and 1, and it so happens that the beta PDF is a distribution that is defined on 0 to 1 unless we shift it. So we'll use a beta distribution as our prior on beta. That's somewhat coincidental. So we tell Dynare that we want a beta PDF. If we had wanted a normal distribution, which wouldn't have made sense for beta, but that would have taken this form with normal underscore PDF. Gamma would be gamma underscore PDF. Inverse gamma is inv underscore gamma underscore PDF. And finally, the uniform is uniform underscore PDF. But we'll use the beta distribution. Next, we need to tell Dynare what the parameters of our distribution are. So we have usually the beta distribution is defined with two parameters, sometimes alpha and beta, sometimes otherwise. In our case, or in Dynare, in the case of Dynare, the first two parameters of the distribution are always the mean and the standard deviation. Now this is close to standard for a normal distribution, where you usually specify the mean and the variance, but this isn't exactly standard for things like the beta distribution. But in our case, we will use the mean and the standard error. This actually allows for some flexibility, or easier specification of our distributions. For instance, we may think that the beta distribution, that beta has a prior with mean 0.99 and standard error of 0.02. And this allows us to not have to go to the to look up the beta distribution to try and mimic that kind of a shape to find the parameters of the distribution that will map to this. Dynare will do that for us. The only exception to this standard is the uniform distribution, where it's more convenient to specify the end points as usual, as is usually done with the uniform distribution. So so with all of the distributions besides the uniform, we specify the mean and the standard deviation first, and then other parameters as needed beyond that. I'll show you an example of that. But with the uniform distribution, say we wanted to do the beta have the parameter beta have a prior with a uniform distribution, then we specify endpoints like 0, 1 as our parameters, and that is standard, although I have made an error here. So the standard way of specifying distributions is that or priors, is to specify the thing that you're estimating, the shape, the distribution that your prior is, and then mu, sigma, P3 and P4, where P3 and P4 are the third and fourth parameters of your distribution. So with a uniform, we would ignore mu and sigma and leave those spaces blank, but we do need to put the commas in between to tell Dynare that we're specifying P3 and P4. So what we should have had before was 0 and 1. Now obviously for the normal distribution we only have mu and sigma. That specifies the distribution. For the gamma distribution, we specify mu and sigma and also P3, which is the third parameter of the gamma distribution. And then for beta, there's an optional P3 and P4 that default to 0, 1. But if we want to shift our distribution and scale it so that it stretches over say 3 to 4 or 3 to 7, we could put 3 and 7 there. But in our case, we want it to be 0, 1, so we'll leave it with the default. And the inverse gamma distribution, just for completeness, only has a mu and a sigma. There's no third or fourth parameters associated with that. Alright, so let's uncomment this line and delete that uniform, and we'll specify beta having a prior distribution of a beta with mean 0.99 and standard error of 0.02. We need to now put a distribution on our standard error of our shock process. Now this we want to have as a strictly positive distribution, so the inverse gamma distribution will match that support, strictly positive support, and we can put a mean and a standard error on that. For instance, a mean of 0.01 perhaps, and maybe we want it to have an infinite standard error, which this allows for that limiting, Dynare allows for the limiting case by using the INF standard way of putting infinity in. Okay, now we've put in our estimated parameters, and we've specified the priors for those parameters. In this case, we'll just estimate these two things for simplicity's sake, and for speed in our algorithm later. Although we could have estimated A or rho or sigma or alpha or delta as well from our using the data from Y. Alright, now we're ready to talk about our actual estimation now that we've specified priors. To do that, I'm going to, just for now, comment out this stochastic simulation command, and we're going to work with the estimation command. This works much like the stochastic simulation or the simul command from our deterministic case, in that we say this, we put this command in, we follow it with a parentheses and a semicolon that specify different options associated with the estimation, and it will do this computation. So this becomes part of our computation block. In the estimation, there are a few things that we always will have to have, and many options that are have default values that you may never need to change. Let's talk about several of these in turn. One that we'll always need to have is a data file. So the command is data file equals, and we put the name of the data file. In our case, that's going to be data. You can see that I've included a data .mat file in the folder where my mod file is. Now Dynare will search for a .mat, a .m, or a .xls file with the name data when I put this command in, or this option in, or whatever I specify as the name there. I don't and I can't and should not put the .mat or .m or .xls extension at the end of the data file name. If you choose to use an .xls file from Excel, you need to be aware that there are some features that you'll need to specify, some additional options that you'll need to specify in order to tell Dynare where to find the data in your spreadsheet. In our case, we're not going to worry about that, but know that that's there, and in the user's guide and and user's manual. They have clearly explained how that all works. I'll leave that to you if you choose to use an Excel file. In my data file, I need to have a variable that has the name of the data, that the observable variable. So in my case, I have data.mat has one variable in it, and it's the y that I am using to do my estimation. And if we load that up, we'll see that it's 2,000 period 2,000 periods of observations on the output, and if we want, we can plot it and see that that's what we've got. Now we'll close that up and ignore that for now, and in fact we'll clear our workspace just for the sake of simplicity. Alright, now let's move back to our estimation command. There are more other things that we need to do in our estimation command. The first thing to talk about after we've specified our data file is to talk about the computation that will take place once we call the estimation command. There are two ways of getting estimates using Bayesian techniques. One is to sample from the full posterior distribution and get an estimate of our mean and our standard error, etc., using that. The other way, and the computationally much more simple way, is to find the mode of our posterior distribution. The reason that's so much simpler computationally is that in finding the mode, it's a simple maximization problem over the posterior. We only need to find the highest point on that posterior. Whereas sampling from the full posterior to find in order to get the mean and the standard error and confidence regions and so on, we'll need to use a Monte Carlo Markov chain technique, and in the case of Dynare we'll use the Metropolis-Hastings algorithm, which takes much more time. So the next thing we'll do is specify the algorithm to find the mode, which Dynare will always do unless we have already done it for it. And we do that with this mode compute command. Now the Dynare offers 6 or 7 different options for the algorithm that it will use to find the mode. The default value for this option is 4, which corresponds to Chris Sims' CS min well function, and that should be fine for what we're doing here. We'll come back to this later and change it once we already have the mode to save ourselves some time. The next thing we will do is that we are going to shut off the rest of the computation, and we'll do that by using the mhreplic command. We'll set that equal to 0. Now the mhreplic tells Dynare how many Metropolis-Hastings iterations to use. Now normally if we're doing the Metropolis-Hastings algorithm, we'll want this to be very large, 10,000 or so, maybe more. In our case we'll do less just to save ourselves time, but this will usually be a very large number. If we set it to 0, then we'll skip all of that computation, which will be useful for us this time. So let's save this and run this command and see and run this mod file using our standard Dynare example, stochastic, and now we have estimation at the end, and we'll see what we get. So the first thing that Dynare has done is plotted our priors, and we can see from this whether our priors are what we'd like them to be. And let's see what else has it done. It has plotted a smoothed version of our shock process, given the estimated values for our parameters and our data, which you'll remember we looked at before when I plotted the observable data. So let's close some of these, including this priors, and see what the printout that Dynare gave us. Through here, we see that the Dynare has done exactly what it has done before, including computing our steady state for us. Now, you notice that we did not declare endogenous variables after the estimation command. That's fine for our case. And you'll also notice that Dynare can't estimate nonlinearized models at this point. So it sets the order equal to 1 automatically so that it will be a linear estimation. Now we'll load our data, and you can see now that it is doing a maximization problem, trying to find the maximization of the likelihood and prior, in other words, the maximization of the posterior. It will find it here and print out the results from posterior maximization. It gives us the prior for C beta, and we have a prior mean of 0.99, like we said. Our mode was 0.9909, so we were pretty close. Our standard deviation of our estimation was 0.0013, and it also gives us a t-stat for that, and then it gives us some more. The prior shape was a beta, and the prior standard deviation was 0.02. And we see the same printout for the epsilon shock process, though our mode was slightly smaller than our prior mean, and we have t-stats there as well. So that has given us that's what the printout and graphs are. Let's look at what has happened over here. You'll notice that Dynare has generated quite a few files for us. As always, we are most interested in the results file, and although we have this mode file, which will just store our mode, that will be useful for us very soon. But let's take a look at our results file. When we load that, we notice that we have a few data structures that are part of that, and just as before, the 00 underscore will be the most interesting one for results. You have endogenous simulations, and you'll see we have posterior mode, posterior standard deviation, and some other results that have to do with smoothing and that we won't talk about here. Alright, so the next thing we'll do is do a more full estimation where we're not just estimating the mode. We'll also try and estimate the mean of the posterior, the standard error of the posterior distribution, and so on. So let's close up our variable editor, and we'll add on to our estimation command in our mod file. To do this, to do the full estimation, we'll have our replications, not our Metropolis Hastings replications, be greater than 0. And like I said before, that 10,000 is probably about optimal, although you'll notice very soon that this is a long algorithm, and it increases as we increase our replications, as we increase the number of chains the Metropolis chains will have, and the number of parameters we have. So we've tried to simplify quite a bit here by only examining or estimating 2 parameters. I'm going to only do 2,000 replications, and I'll only do 2 Metropolis chains in order to keep the estimation to a manageable time for the time we have. One thing we can do now, though, is skip the computation of the mode by setting the option equal to 0. Now, Dynare will still need the mode, but we have this mode file that I pointed out before that stores that for us. And in fact, we will just tell Dynare that the mode file is the example underscore stochastic underscore estimated underscore mode file that it saved for us before. And now we will be able to skip all that computation going forward. Along with our replications, there are many, many options that are associated with this Metropolis Hastings algorithm. If you're not familiar with the Metropolis Hastings algorithm, I suggest looking it up and becoming familiar with it, because there are some critical choices in what we'll do now that will really affect our estimation process, and understanding the Metropolis Hastings algorithm is critical in understanding what's going on here. To diagnose the convergence properties of our algorithm, we'll specify that there will be 2 blocks, Metropolis Hastings blocks, which corresponds to having 2 different runs of the Metropolis chain that we can compare across. We'll also specify a burn-in period, and it's very convenient in Dynare that we can specify a percentage burn-in as opposed to a fixed number that we'll burn in with. For instance, we'll use 10% burn-in, so that will drop 200, the first 200 observations of our 2,000 long chain. The default in Dynare is 0.5, so dropping the first half, which may or may not be too strong and too wasteful of these draws. The last thing that we need to specify is the Mhj Scale Parameter. Now the J-scale parameter is the scale of our jumping distribution. This corresponds to something like a scaling of the variance-covariance matrix of the jumping distribution, which will be multivariate normal. Now the default here is 0.2, though that is almost never going to be adequate for your estimation. The way to diagnose this is to observe your acceptance rate, which will be very easy to do, as you'll see very soon here. In our case, 2.5 will be close to will give us an acceptance rate that is close to 25%. Generally, you want your acceptance rate to fall between 25 and 50%, though that is not an exact science. So this should be enough for now in terms of our estimation, or specifying the options for our estimation for the Metropolis-Hastings algorithm. So let's save that. We'll come back over here and let's once again clear our workspace just so we can more easily see what is happening. We can start our estimation again and we'll see what happens. I've put the wrong name in my file. Again, this illustrates the very useful error checking. I know that it's in my mod file and it's between the 90th and 98th characters. So mod file line 55, 90 and 98th characters. Let's go over, and no surprise it's in the estimation command. And we come down and find that columns 90 through 98 are right here. Mh blocks. Actually the command is mh underscore n blocks, so number of blocks. So we'll save that and once again clear and run our estimation. Once again I've run into a problem, and it appears that I've specified the wrong name for my mode file, and that's easy to see that I just spelled example wrong. Most of you probably caught this as I was doing it. So let's close up our figure here and come back and change the mode file name. Yeah, there it is. Save it, and we can probably run it for reals this time. Let's watch. You'll note the priors are the first thing that are observed, or that are plotted, and then next it tells us the results from the posterior maximization, although this time it didn't do the computation, it just pulled it from that mode file. And now we start the Metropolis-Hastings algorithm. Metropolis chains, we've started multiple chains. It finds initial values for us, and it starts the Metropolis-Hastings algorithm. You see that we're on the first of two chains. This is the progress, also illustrated by the movement of the red progress bar, and we can monitor our acceptance rate, which is around 20% right now, which is actually a little bit too low. So we'd need to adjust our Mhj scale option for this. But it's actually probably going to be okay. For now, I won't worry about restarting this. But you'll see that even with only two parameters to estimate, or only two things to estimate, one parameter and one standard error, and with only 2,000 iterations or replications of our Markov chain, we're still only doing the first chain. So you'll see now it's started again. We have our second chain going, and I'm going to take a break while this continues on, and we'll come back at the end of this algorithm. Alright, we're about 90% of the way done through our second algorithm. You'll see that our acceptance rate is close to 25% this time. We're through the second chain now, just about, and there we go, and we'll generate some plots that we'll go through, as well as some printing some results in our command window. The first thing to notice is that this took 3.5 minutes just for this length of a Metropolis-Hastings algorithm. So don't be surprised when you have, for a larger model, a more realistic large-scale DSGE model, and where you're estimating many parameters, that this might be an overnight job to do this estimation. Don't worry that your computer is just too slow for this. It's actually more a function of the algorithm itself. Let's begin by looking at the rest of the output in our command window. So after it found initial values, it says that it's generated one Metropolis Hastings file per block, two files, and 2,000 iterations. It then tells us the acceptation rate. And the first one, it was a little low at 20%, and the second one, it was almost at 25%. So that's pretty good. Does some Mcmc Diagnostics for us. The Brooks and Gilman 98 convergence diagnostic. It computes both of those. I won't go into those here, to what that actually is here, but you can certainly look that up. We have 2,000 draws. We generate one Mh file, and at Mh file number 1, we start at line 200 because we are only keeping 1,800 draws. It computes the mean, and the posterior mean and covariance, and the log marginal density, or in other words, the posterior probability of our model in general. This will be a useful thing if we're comparing different models. And furthermore, we get some estimation results. We get our log data density, and then our posterior mean and mode. So we'll see that our prior mean of 0.99 and our posterior mean were pretty close. We have a confidence interval. Now that's a 90% confidence interval. That's the default. I'll show you in our next run of this how to change that to a 95% confidence interval or a 99% confidence interval, and so on. And our prior distribution and prior standard deviation. And once again, we have the same printout, except for our epsilon shock. One thing I want to point out before going through the graphs is that we have this folder up here that's associated with this mod file after we've run the file, and this shows up every time, whether you're doing a simulation or a stochastic simulation or whatever. But let's open it up and notice that there's a subfolder called Metropolis. In that folder, you'll see that we have these block 1 and block 2 data files, and you'll notice that they have 2,000 by 2 data series in them, and those are exactly corresponding to the 2,000 draws, Metropolis Hastings draws, for the two things that we're estimating. This will be useful because if we want to go back and do more draws, it would be inefficient to start over. Say we want to do a 10,000 draw estimation. Well, we already have 2,000 perfectly valid draws. It will be helpful and save us a lot of time to just add on to those 2,000 as opposed to starting over. So I'll show you how to do that coming up next. So we'll navigate back to our folder that has our mod file in it, and let's look at the figures that Dynare has printed. We know about the priors. We know about well, now we have some diagnostics. So we have this univariate diagnostic. Again, this is the Brooks and Gilman 98 diagnostic. Again, I'm not going to go through that here, but you can see that we have the plots of those. We also have the monitoring plots for our distributions. It only obviously, well, it plots the last 1,000 here. We also have plots for our prior and posteriors. So let me make this larger so we can see it a little better. For our standard error, this gray line was our prior, and our posterior is this black line, and the green line is the posterior mode. You'll notice that we're nearly symmetric here. And similarly for beta, the gray line was our prior, where we're not seeing a huge spike at 0.99 that actually is what our prior looks like. But we are seeing the posterior in black and the mode in green. So those are useful plots. We'll notice here that probably our prior was not well specified, and we may want to change it to do some sensitivity analysis to see if our posterior is sensitive to this prior that is not nearly congruent with our what we're finding in our posterior. Let's close that, and lastly we'll have our smoothed variables for epsilon and our data y. Okay, let's go back to our editor now, and this time I want to show you how to add on new draws without having to replace the old ones. To do that, all we'll do is at the end specify the option load mh file. This will load those files that I showed you earlier, and then it will add on this many replications on top of what we've already done. So if I ran this, we'd end up with 4,000 observations. The nice thing about this burn-in as a percentage is that Dynare will then do the estimate, find the means and covariance and so on, dropping 400, the first 400 observations as opposed to the original just 200. So it will update that automatically for us. Once again, we're saving ourselves time by not computing the mode and by not starting over. So why don't I run that? We'll save it and then come over here and run this again, and you'll see it. You'll see Dynare start up, and then I'll spare you from watching the red bar go across. Just know that it will run it again for 2 times, and also notice that we've loaded past Metropolis Hastings simulations, all 2,000 of the ones that we've done before. So we'll take a break now and come back when this algorithm is. Alright, we're coming to the end of our second chain here. We've just added 2,000 draws, Monte Carlo draws, and we'll see that that is reflected in our graphs. We won't go through explaining the graphs again, but we can see that now we're going up to 4,000 draws, where we've only had to do 2,000 extra draws because we've added them on top of what we've originally done. There are only a few other things that to talk about with our estimation, and the first is that the initial values for the Monte Carlo, the MCMC algorithm, are defaulted to the prior means that we specify for each parameter. Now, if you want to initialize it at something other than the prior mean, we can do that by adding an estimated params init block. Init block, and we do just what we've done before, and that is put a comma and then an initial value. Now if we were to put 0.99 there, it would be superfluous because our initial value is going to be 0.99 from the original, because it's the prior mean. But if we wanted to say start at 0.95, we could do that, and the standard error of epsilon being 0.01 would be the default, but we notice that our prior or posterior mean is somewhat different from that, so what if we started somewhat higher at 0.06. Similarly, we may have bounds on our parameters. For instance, we may want to have a truncated prior. So maybe we believe that the distribution that we want for our beta is normal, but that we don't want it to go below 0 or above 1. So say we changed this to a normal.pdf, and then we specify the initial, the estimated params bounds block, and we would write C beta, and then the lower bound, and then the upper bound, 0, 1. That's that can be useful in your estimation. We won't include those here because we've already done 4,000 draws, and we don't want to invalidate those at this point by starting over. We'll just go ahead and save that as what it was before. I did tell you that we could change the significance level that's reported in our output. Let's do that now. It's the conf sig option, and the default is 0.9 for a 90% confidence interval. We can change it to, say, 0.95 if we would like. To do this very quickly, let's just set our replications down to 0 again, and we'll add 0 replications to the 4,000 we already have. Note that we still have this load mh file command so that it will use those. So let's save that and rerun our observation. Oh, unfortunately, luckily I didn't do any extra draws, but you'll notice that I now have a normal distribution on my beta, and this would have been a problem because I would have been sampling very likely way outside the 0-1 range. So we'll go back and fix that now, but before we do that, note that our posterior standard errors that aren't reported here, but will be reported over here. So we have the estimated mean, the mode file, Metropolis Hastings mode, the regular mode, and then obviously our results file. In our results file, though, we can come over and look at what's in OO and look at posterior mean, posterior variance. The deciles are going to be the let me open one up for you. So it splits it into parameters versus shocks. We have one parameter and one shock. Let's look at beta, and we'll open that up, and you'll see that we have the 10%, 20, 30, 40, 50, which is the median, 60, 70, 80, and 90% intervals. Closing those up, we can also, it looks like we actually need to have at least one draw before it will actually output those that confidence interval. So let's make the change back to a beta PDF, and we'll just do one replication, save it, and run that, and you'll see that this goes very quickly. We have one draw from our Metropolis-Hastings algorithm, and nothing really has changed. And now we have this confidence interval being a 95% confidence interval. Really the last thing to talk about, although there are many other options that you can do, is to talk about computing simulations given our posterior distribution as opposed to our just our initial values that we had set originally. Alright, the last thing we'll do is first of all clear everything, and I'll show you that we can estimate our impulse response functions with Bayesian IRF, and we can get the Bayesian estimation on our IRFs. As always, the IRF command defaults to 40. We can make it 50 or 60 or whatever we want it to be. We'll save that. We'll run our Dynare file, our mod file. Let's go ahead and set our replications equal to 0, so we can skip out on that this time and go ahead and run that. Now you'll see when we do that posterior IRFs will be computed for the 8 endogenous variables of your model. This can take very long. Now this is generally true. In our case, we have such a small number of parameters we're estimating, and our model is so simple that this won't be a problem, but in general this can take a very long time. You can it will ask you whether you want to consider all the endogenous variables or just the observed endogenous variables, or stop Dynare and change the mod file, because this can take very long. We'll go ahead and just do number 1, consider all the endogenous variables, and you'll see that it will compute the posterior IRFs for us and plot them, which is nice. Now unfortunately there's a bug with Dynare where that plot gets shut down immediately after it plots it, but I will open it up I can regenerate it pretty quickly. So let's go ahead and do that. We'll open it up. You'll see that we have this posterior IRFs now that we can use, and we'll go ahead and plot those. And you can see this is our posterior, ignoring this last plot, but we have our posterior with 90% confidence bands, Bayesian confidence bands around the IRF. You can see them most clearly with C here. Anyways, that's a very simple thing that Dynare takes care of for us, and it can be a really useful tool with one simple command. The last thing before I go that I want to mention is this, that I have been using a separate MATLAB file called example_stochastic_estimated_steady state, and it's an M file that is computing my steady state for me. You recall that when we were talking about computing steady states before, I had the I just had MATLAB or Dynare find the steady state for me. Now this can take a long time, especially given that with our Metropolis-Hastings algorithm, every time we draw from the posterior mode, we need to update our steady state, or our posterior distribution rather, sorry. Every time we take the draw, we need to update our steady state. Now that means we'll spend 90% of our estimation time computing the steady state if we're having it find the steady state for us every time. If we can specify this steady state file that just needs to have the name, the same name as the mod file _steady state, and help Dynare find the steady state by passing it some values. And I'm not going to cover that here, how to write that file, but you can find help on the Dynare website in their forums. There are some great examples of how to do that, how to write that file, and that cuts down on the computation quite a bit. Alright, to review, what we've done here is covered Bayesian estimation with Dynare for parameters, the standard errors on our shock process, and while we haven't covered it, we can also do that for the correlations between two variables. We've talked about doing estimating the posterior mode and using Metropolis-Hastings algorithm to find the posterior distribution. And finally, we've covered the Bayesian estimation of our impulse response functions. All right, that's it.